In the previous lecture, we saw some basic results related to compactness. We now explore how compactness behaves with continuous maps. So, proposition that f from x to y be a continuous map the image of a compact set is compact. So we are obviously giving the image the subspace topology from Y. So proof. Let Z contained in X be compact. And let us take an open cover of f of Z. Be an open cover. So then this means that Z is contained in union F inverse Vi. So as Z is compact, this has a finite subcover. So this implies that Z is contained in union I j equal to 1 to n F inverse of V I sub j. So which implies that f of z is also contained in this finite subcover. So this proves the proposition. This completes the proof. So the following proposition is very useful. So let f from x to y be a bijective continuous map So if x is compact, then f is a homeomorphism. So proof. So let G be the set theoretic inverse of f. So to show that G is continuous, it suffices to show that if Z contained in X is closed, then f of Z is closed in Y. and being a closed subspace of a compact space, so this implies Z is compact. This implies f of z is compact. This implies f of z is closed in Y. Because we use the result that compact subspace of a Hausdorff space is closed. So this completes the proof. So we will not prove the following important theorem. Let xi be compact topological spaces. Then product of xi is compact. So this is Tikhonov's theorem. So those interested in a proof may consult Munkres. So next we come to metric spaces. So we have the following useful characterization of compact metric spaces. So theorem, let X be a metric space then X is compact if and only if every sequence in X has a convergent subsequence. So let us prove this. So first assume that X is compact. So let S be equal to Xn be a sequence in X. So if S is finite, then there is, so if S is a finite set, then there is some X in S which is repeated infinitely many times. And so we are done. We can take this subsequence. So therefore, let us assume that. So let us assume that S is infinite. So without loss of generality, we may assume that the xn's are distinct. So let y be equal to S closure. So if y minus S is non-empty, then we are done, as this implies there is x naught in y minus S and a sequence of points x and j converging to x naught. So we assume that y is S closure is equal to S. So if xn is any point in S and there is a subsequence converging to xn, so for instance we could have a situation like this. So this point could be x1, x2, x3, and we have a subsequence converging to x3. So then again we are done. So therefore assume that there is no subsequence converging to xn. But this implies that there exists delta n such that the open ball p delta n around xn intersected with S contains only xn. So as y, this S closure, this is equal to S, is a closed subspace of a compact space, so this implies that y is compact. But we can write y as union n greater than equal to 1 p delta n xn. So this is an open cover. So intersected with y is an open cover which has no finite subcover. Which is a contradiction. So this proves that. So this shows that S has a convergent subsequence. So next let us prove the converse. So we assume that in X has a convergent subsequence. Then we shall show that X is compact. So we take open cover of X. So we will prove two claims. So claim 1, there is delta greater than 0 such that given any open set B delta X, there is some I such that B delta X is contained in UI. So proof of claim 1. So if claim 1 is not true, then for each n greater than equal to 1, there is an xn such that B delta, well, delta is 1 upon n, so that B 1 upon n xn is not contained in UI for any I. So we let S denote the sequence of these xn's. Then by our hypothesis, there is a convergent subsequence xnj's converging to x0. So there is some u0 such that x0 belongs to u0 and some epsilon greater than 0 such that B epsilon x0 is contained in u0. So u0 is like this, and then here we have x0, and there is this open ball which is contained in u0, and we have a sequence of x and j is converging to x0. So for j very large, x and j belong to B epsilon by 2 x0, and if j is very large, then 1 upon nj is strictly less than epsilon by 2. And it is easily checked that P 1 upon nj x nj is contained in B epsilon by 2 x n j, this contained in b epsilon x naught, which is contained in u naught, which contradicts the assumption that b1 upon nj x nj is not contained in any ui. So this proves claim 1. So using claim 1, we will prove claim 2. There is a finite subcover of X. So proof of claim 2. By claim 1, there is delta such that for every open set B delta X, there is an open set UI such that B delta X is contained in UI. Thus, when we look at B delta by 2X closure, this contains B delta X. This is going to be contained in UI. So now we choose any y1 in X and let x1 be equal to b delta by 2 y1 closure. So assume that we have defined xn. So we are going to describe how to inductively construct these sets xn's and define xn plus 1 as follows. Choose yn plus 1 in x minus xn and define xn plus 1 to be xn union b delta by 2 yn plus 1 closure. So we have our y1. So this is x1. Then we choose y2 outside this. The union of these two is x2. Then we choose y3 and so on, and we go on. So then x1 is contained in x2 is contained in x3 and so on. So this has to stop infinitely many steps, or else the sequence yn's has no convergent subsequence as the distance between yi and yj is always greater than or equal to delta by 2. So thus x is covered by finitely many b delta by 2 yi's closures, but each of these is contained in some uj. So thus x is covered by finitely many uj's. So this completes the proof. So, so this completes the proof of the theorem. So we will end this lecture with the following useful lemma. It's called Lebesgue number lemma. So let X be a compact topological space and let X, and suppose we are given an open cover UI, then there is delta positive such that every open set of the type is contained in some UI. So proof, as X is compact, there is a finite subcover and we may assume, and so we may assume that X is the finite union of these open sets. So let Ci be X minus these sets. So these are closed. So define a continuous function on X. So f is from X to, the image actually lands inside R greater than or equal to 0 a priori. The distance of X from Ci, and we sum all of them. So then f is continuous as each dci is a continuous function and this function never takes the value 0, as f of x is equal to 0 implies dci of x is equal to 0 for all I implies x belongs to ci for all I, which is not possible. As intersection of ci is empty. So as x is compact, this implies f of x is compact. This implies f of x is closed in R. As 0 does not belong to f of x, this implies there exists delta such that f of x is always greater than or equal to delta for all x. So this implies that dci of x is greater than or equal to delta by n for at least one I. So this implies that b delta by n x is contained in ui for some I. So this completes the proof of the lemma. So we will end the lecture here.